Okay, we just finished talking about angular displacement. Now we're going to talk about angular velocity and angular acceleration. So angular velocity. Angular velocity is how fast something rotates. Okay? If you remember, linear velocity was how fast something moved. It was a distance over a time, okay, or displacement, a linear displacement. So now we've got an angular displacement, which is an angle, so the angle that it rotates through, okay, divided by the amount of time it takes. Okay, it's still a vector, just like linear velocity was a vector. It includes a direction. The counterclockwise direction is the positive direction. Okay, again, that's because of our unit circle. When they made the unit circle, it was made so that the positive direction was going counterclockwise, and therefore the clockwise direction is negative. Okay, now when we talked about linear or angular displacement, we use the Greek letter theta to represent the unit, or the symbol, sorry. So again, we're going to be using a Greek letter for the symbol. This time we're going to use the Greek letter omega, and when you think omega, you might think like omega health around this area, and then you think of the capital omega, which is used to represent the unit for ohms, okay? But this is omega as well. This is the lowercase omega. Basically, it is the lowercase w, but curled in on the sides a little bit. Okay? The units for angular velocity, well, it's how fast something rotates. It's the angular displacement, which we measured in either degrees, radians, revolutions, or rotations, okay, per unit of time, so minutes, seconds, hours. Okay, so some examples. Radians per second, radians per minute, revolutions per minute, or RPMs. You have probably seen that one in your everyday life. Okay, now the equation. Well, go back and just think about the linear equation. Okay, when we're talking about constant motion, something that's not accelerating, we said that the velocity or the speed, okay, in this case we use omega, was equal to the displacement, in this case the angular displacement, so theta, over the change in time. Okay, now again, this is only for constant motion. Okay, you cannot use this equation when the object is accelerating. Okay, in this case, not linearly accelerating, but angular acceleration. It's not speeding up or slowing down to use this equation. Okay, then we've got angular acceleration, and this is going to relate very similarly back to linear acceleration. Okay, it tells you if something is rotating faster or slower. Okay, so maybe it's rotating, starts off from rest. Okay, and it has an angular acceleration of 2 radians per second squared. So after 1 second it's going 2, after 2 seconds it's going 4, then after 3 seconds it's going 6. Okay, it's speeding up. It could also be slowing down. Okay, it is a vector again. Okay, positive is counterclockwise in direction, negative is clockwise in direction. The symbol again is a Greek letter. It's the Greek letter alpha. Okay, it looks kind of like that. All right. The units are radians per second squared or revolutions per second squared, or you could combine them, revolutions per minute per second. Okay, but again, just comparing back to linear motion, it is your displacement divided by a time divided by another time. Okay, and again, it's going to tell us if something is rotating faster, it could be speeding up, or it could be slowing down. The equation, relate this right back to your linear motion again. Okay, so linear acceleration was the acceleration, and again I'm going to convert it, so we're going to say the angular acceleration is the change in velocity, but the change in angular velocity over the change in time. Okay, and then you can go ahead and find your angular acceleration using that equation. What you are going to notice is that we can use all the same equations that we used before. We simply need to change some units. Okay, our displacement before when we were in linear motion, we used the variable x. Okay, now we're going to use the symbol theta. Where we had linear velocity v, we've got angular velocity omega. Where we had linear velocity a, we've got where we had linear acceleration a, we've got angular acceleration alpha. So you'll notice if you look at the equations, you just simply substitute omega for v. Okay, theta for x. Okay, time is time in both. All right, but you can do that with all of the equations. Again, you need to be careful with the first equation. These ones are only for constant motion. Okay, cannot be used when the object is speeding up or slowing down. Okay, the rest of these, as long as we got a constant acceleration, we're good to go.